This is the, let's see, 1, 2, 3, 4, fifth video that you should watch at the beginning of this course. You might be starting to wonder, how many videos do I have to watch to get started and keep going in this course? It's the big amount here is at the beginning, okay? For the most part, on average, there's going to be about 1 video per section, sometimes 2, but for the most part 1. It's at the initial start of this course where you're sort of watching a lot because we want to just tell you a lot of information to get you going on things. I'm going to try to keep this one short, but you'll notice I'm wearing the same clothes as video number 4. That's because we just finished video number 4 about a minute ago. So we're starting video number 5. In video number 5 here, I do want to keep it shorter. I want to focus on this rabbit-fox predator-prey model from the very first section of the book. Think of R as representing rabbits and F as representing foxes. And T is time as always. And we're assuming, we're hypothesizing that rabbits and foxes are going to interact, that the foxes are going to eat the rabbits. Again, evidently that doesn't really happen in nature, but it's kind of fun for the purposes of doing this to pretend it does. This model is two-dimensional. There are 2 dependent variables, 1 independent variable, t, 2 dependent variables. There are actually differential equations where you have more than 1 independent variable also. Those are called partial differential equations, and I will have some Mathematica extensions where you can play with partial differential equations, but we're not really going to study them in this course. That's for another course. You might encounter that in a course like Mathematical Methods in Physics, where you do some partial differential equations. So we're coming back to ordinary differential equations with ordinary rather than partial derivatives. But in this case, we do have 2 dependent variables and 2 differential equations. 1 for the rabbits and 1 for the foxes. We'll see when we get into chapter 2 that it's quite often useful to think of these kinds of systems of differential equations in terms of vectors and what are called vector fields. That is a real good perspective to have on these systems. But for this first section, we're just treating it as 2 scalar equations. So what should we assume? How should we construct our model? Well, you've done the reading perhaps, and you might remember. See if you can kind of think about it for a second here and try to remember without looking in the book. Okay, you might want to pause the video. Are you back now? Maybe. Okay, well, now you want to be back. What should we do with the rabbits? Well, you know, rabbits reproduce pretty quickly. And I don't think it takes much for them to find some food. They're pretty good at digging up in people's gardens and so forth. So the rabbit population, you might assume if there were no predators, no foxes around, that they would grow pretty fast. And they do. They reproduce pretty quickly. Probably good to assume exponential growth for the rabbits, at least in the absence of foxes. Using a Greek letter here, alpha times r. I could have used k times r like the US population model. But I'm using a different letter, alpha. But it is a positive constant. All my constants in here, all of my parameters are going to be positive. This is telling me that the rabbit population would grow exponentially if I ignored predators. But of course, the point of this is to not ignore predators. So how do I model the effect of the predators? There's lots of things you could try. Right? You might subtract a constant from this, essentially meaning that the predators are eating the prey, the rabbits, at a constant rate over time. Is that realistic? I don't know. You'd have to test it out and see. Evidently, it's maybe not quite as realistic as it could be. It turns out to be better to try to model how the foxes affect the rabbits by how often they interact. How often do foxes eat rabbits, in a sense? You know, the more rabbits there are, the easier it's going to be for the foxes to catch them. Okay, you know, if there were millions of rabbits in a small area, the fox would hardly have to do much work to catch a rabbit. So somehow I think the rate of decline of the rabbits must also be related to how many rabbits there are. Probably also how many foxes there are. The more foxes there are, the more the rabbit population is going to decline. And that's what we do. If we write the term like this, a constant, beta times r times f, that's a quantity, ignore the minus sign for the moment, that is big, or gets bigger, you might say, if r gets bigger. More rabbits, the more they die off. It also gets big if f gets bigger, assuming beta is positive, like I'm assuming here. The more foxes, the more it affects the rabbit population. Put a minus sign here because the effect on the rabbits is negative. That effect causes the rabbit population to decrease in size. They're still reproducing, but there's also these rabbit-fox populations that cause some rabbits to die. Is this a good idea? Is this a good model? You don't really know until you just try it out and compare it with real life. What about the fox population? Well, even though foxes might eat other animals like rodents, we don't want to get too complicated here initially. We're just trying to look at the, maybe ours should be rodents. A thought just popped into my mind, okay? Maybe that would have been better. But, okay, we're ignoring everything else. We just got rabbits and foxes here, okay? And so, while foxes do have other sources of food, we're going to assume if there's no rabbits, that the fox population dies off, sad to say. They don't have the food they need. How should we model that die off? Well, again, you could try different things. We're actually going to model it as an exponential decay. There's going to be a constant negative gamma. It's supposed to be a gamma. Looks like that. Negative gamma times f is going to model an exponential decay in the fox population if there are no rabbits. But of course there are rabbits, and we want to take them into account. The effect on the rabbit population on the fox population is good. That's a positive contribution. We're going to model it like this. Now, you can do lots of things with this kind of equation, and that we will do it through the entire course. For example, one thing we'll do in Chapter 2 is talk about how to write it as a vector equation, talk about something we call the vector field, and come up with a numerical method called Euler's method to approximate solutions to this. Right now, we can still do some things with it. We can factor these expressions on the right-hand sides, for example, as much as possible. Like that, for example, to find what are called equilibrium solutions. Just like the logistic model, and in fact also the exponential model had equilibrium solutions. The equilibrium solution for the exponential model was the constant function at 0. The logistic had 2 at 0 and n. This two-dimensional system has equilibrium solutions also. But they're not constant functions in the usual sense. They're constant functions in a higher dimensional sense. If you set both of these equal to 0 and solve for ordered pairs, for example, the ordered pair RF equals 0, 0, and think of that as a constant function where the output is a constant point, if you will. That would be an example of an equilibrium solution. Don't think about graphing it in the usual way. Just imagine that as being a function of t, but a constant function of t. It's always giving you an output equal to this point. That's going to make both the right-hand sides equal to 0. But also, if you think about it a little bit and read the book, if R is gamma over delta and F is alpha over beta, those will make these things 0, making both right-hand sides equal to 0, making, therefore, both derivatives equal to 0. And if it starts at 0, it's going to stay at 0. And so this point, thought of as a function of time, a constant function of time, is also an equilibrium solution. These are the equilibrium solutions to this system of differential equations. And you can plot them in something called the phase plane as points. Now, when you think about this diagram, I'm drawing them as points, and sometimes we'll see that we will call them equilibrium points. But in fact, in your head, you want to imagine those as being functions. They're constant functions of time. Turns out, either by using computer programs, or by thinking about the signs of dr dt and df dt, where are they positive, where are they negative, based on where these things are positive and negative, I'm not going to go into detail here, you can figure out basically what solutions look like in the first quadrant, which is the relevant quadrant, because that's where both R and F are positive. And it turns out that they look like this. They kind of rotate around the equilibrium point, equilibrium solution, that one right there. That's this point right here. They are what we call periodic solutions. And if you graph both R and F versus time, it's even a bit more interesting. You'll see this in the text. You get periodic graphs there, not exactly like sine or cosine waves. They don't have the exact same kind of shapes. But they are still periodic. They repeat themselves exactly. And an interesting pattern emerges. Let's pretend the red here, not sure how well that's showing up. Is it showing up okay? Zoom in if you need to. Let's pretend the red here is rabbits. And then the black that I make is foxes. You might see something like that for the rabbit population. Turns out what you see for the fox population is a similar kind of wave, not necessarily of the same amplitude though, and these are not necessarily circles, even though I kind of drew them like circles. In fact, in almost all instances, I'm pretty sure they're not circles. They tend to ultimately be a little bit more like this, I suppose you might say, sort of flatter near the axes is one thing that happens with them. And they are parametric curves. You want to imagine going around and around these in the direction of the arrows as t increases. So the arrows indicate the direction of the solution curves, how R and F change versus time as time increases. But coming back over here, you'll see a very similar kind of thing, again, maybe with a different amplitude. But there will definitely be a phase shift. These won't be in perfect unison with each other as far as exactly where the peaks and valleys are. There'll be a little shift to it. And the cool thing about this model is that kind of makes sense. It should make some intuitive sense to you that the rabbit and fox populations are not exactly in phase. Why? Well, think about it. If they're both low to begin with, there's not a whole lot of rabbit-fox interactions. The rabbit population is going to increase, perhaps pretty rapidly, up toward a maximum. But when it starts getting pretty high, there's lots of rabbits around. There's lots of food for the foxes, and that high value of R is going to cause the fox population to increase pretty rapidly. And it still continues to increase even past the point where the rabbits start declining, because there's still lots of rabbits for them to eat. And the fox population really only starts declining once the rabbit population gets low. Now the rabbit population is low, the fox population is declining rapidly because there's not much food. And once the fox population gets to a certain point, real low, then there's not many predators, so the rabbit population recovers. And this kind of phase difference in these periodic curves is one of the more interesting things that happens in this model, and it confirms common sense. Models don't always confirm common sense. Sometimes they tell you surprising things. And that's where the real excitement occurs. But I think at first, when you're doing real simple models, it's nice that they confirm common sense. Then you sort of get more confidence to try to build more complicated models. Final point that I'll make is that make sure when you read section 1.1 and work on the Mathematica file, if you haven't already, that you also think about how these differential equations kind of, in a way, this is only in our imaginations, they kind of communicate with the solution curves. That's a way to imagine it, at least. It's not, of course, literally happening. But a way you can imagine, a very fruitful way of imagining differential equations, is to imagine that these equations communicate instantaneously, continuously, with the solution curves. One way to view it is that they tell the solution curves what kind of slope to have, in a sense, if you're thinking about these functions over here. How fast to change. That's what derivatives are all about, their rates of change. Another thing that you'll read about, just that I want to mention very quickly, is that sometimes people think about these equations in what's called differential form. In essence, you pretend that you can multiply both sides by dt to write the equations in this way. That's what the first equation becomes, and here's what the second equation becomes. If you see equations like that, those are really differential equations too. Now, from the perspective of standard mathematics, you can't literally say I'm multiplying both sides by dt to get these equations here. But lots of scientists go ahead and imagine it that way. And there's two reasons that's good. One is it helps them get right answers. Okay, it turns out to be a technique that quite often can be used to give you right answers. And another reason it's good for many scientists to think this way is it helps you understand how differential equations model change in another way, which also ends up leading to numerical methods for approximating solution. This Euler's method is, in essence, based on thinking about the differential equation this way. And when you look at these equations, how should you then think about them? Let's focus on the first one. Think of dr and dt as being little tiny changes in the rabbit population and in time. Of course, if we're going to imagine really tiny changes in the rabbit population, we probably have to have millions of rabbits as far as our units go to truly imagine really tiny changes in the rabbit population. Essentially, what this kind of equation, this differential equation, can tell you, if you think about it intuitively, is this. Imagine a small amount of time goes by. Not in this, something as small as a second, but I don't know, maybe a few days or something, if the regular scale is years. If there are millions of rabbits, or even billions, okay? You can replace dt with that small change in time. And if you happen to know all these numbers, alpha, beta, r, and f, at the instant in time you started with, the idea is to plug those numbers in there, multiply the result by dt, and you hope it's pretty close to giving you the answer for how much the rabbit population is changing. If dt itself is very small, dr will also be very small. But you're still going to get a number out. And the hope is that that number is going to be accurate enough that you could still use it. And that's another way to imagine the communication between the equations and the curves, is that these equations tell you how much the dependent variables change, what little amount they change by, if the independent variable changes by a very, very small amount. And that's the end of this video.